In the last two videos, we learned about how to use moles to convert between two different types of measurements for the same substance. Counting numbers, e.g. X number of atoms or X number of formula units, and mass, grams of an element or grams of a compound. Specifically, we looked at silver atoms being converted into moles and grams of elemental silver, and moles of sulfur sulfide molecules being converted into moles and grams of sulfur sulfide. In both cases, when we interconverted, we were working with pure substances. Elemental silver is a substance, an element that only contains one type of atom. Silver sulfide is also a substance, specifically a compound. It contains two elements, silver and sulfur, that can be expressed as a single chemical formula. It doesn't work to convert between grams of two different substances. But when we use moles, are we limited to staying within one pure substance? No, we're not. And that's where the beauty of stoichiometry comes in. Stoichiometry is the ratio in which elements combine, both in compounds and in chemical reactions. So far, we've seen stoichiometry come into play through subscripts in chemical formulas, the mole, with the atomic mass of an element, the molar mass of a compound, and in this video, we'll see stoichiometry also come into play with the coefficients in chemical equations. When we convert a substance into moles, it's a universal unit that allows us to interconvert between different types of substances. But why do we care about this? Let's go out west and find out. The town of Telluride, Colorado in the Rocky Mountains is a very popular ski destination. Telluride got its name because it was a gold mining town. But the gold here didn't occur as plain old elemental gold or Au solid. It was a compound of gold and tellurium together, gold telluride, known as calaverite. Before the gold could be used in jewelry or currency, though, the tellurium would have to be separated from the gold. If miners knew the chemical formula of the gold telluride, which was AuTe2, they could back calculate how much gold was in their sample and therefore how much money they would make. How does it work? Well, let's take a look and start with gold telluride. The chemical formula of gold telluride is AuTe2. If we remember back to chemical formulas, the subscripts tell us how many of each atom is in one formula unit of the compound. Pause the video and determine how many atoms of gold and how many atoms of telluride tellurium are in one unit of AuTe2. The 2 on the Te tells us we have 2 tellurium atoms in one formula unit, and the lack of a subscript on the gold tells us that we only have 1 gold atom in a formula unit. So where do subscripts become useful in terms of moles? Well, it allows us to build a relationship between the elements that make up a formula unit and the formula units themselves. Let's start back at the beginning with numbers of atoms and formula units. So let's say that we have 1.6 times 10 to the 23rd formula units of AuTe2, or that many individual molecules of AuTe2. If we have that many molecules of calaverite, how many Te atoms are in the same sample? I'll give you a hint that it involves dimensional analysis, and you might want to use the conversion factor you just calculated. Pause, give it a try, and I'll walk you through. So we start with 1.6 times 10 to the 23rd formula units of AuTe2, or gold telluride. Let's look back at our coefficients. How many Te atoms are in one molecule? So we can use that relationship, but remember, we want our units to cancel. So we would put 1 unit of gold telluride at the bottom and 2 units of telluride at the top. Formula units of gold telluride cancels, and we end up with 3.2 times 10 to the 23rd telluride atoms. So going back to the mole map, if we have a certain number of formula units, multiplying the number of formula units by the subscript of the atom in the chemical formula can give us the number of individual atoms in a particular element in that molecule. You can also go the other way around. It turns out that the same relationship applies to moles too. So let's say you have 0.35 moles of gold telluride. How many moles of elemental telluride are found in that sample? Pause and try on your own. The calculation will be set up exactly the same. except we would start with 0.35 moles of gold telluride, multiplied by 2 moles of telluride on the top, 1 moles of gold telluride on the bottom, moles of gold telluride would cancel, and we end up with 0.7 moles of element. So we can write the same relationship here with the subscripts in the chemical formula and will allow us to interconvert between moles of compound and moles of elements that make up the compound. Sweet! Now let's say you're a miner who has harvested 500 grams of gold telluride, and you want to know how many grams of gold are in your gold telluride. How would you do this? Pause and take a try. It turns out that you can't go directly from grams of one to grams of the other. If you just try to use the stoichiometry in grams, you would get more than 500 grams of gold and 500 grams of gold telluride, which is physically impossible. This is where the mole becomes valuable. Take a look at the mole map we've been constructing this whole time. Do you see a route to get from grams of gold telluride to grams of gold? Yes. We would convert grams of gold telluride to moles of gold telluride using the molar mass. Then we would use stoichiometry. 1 mole of Au comes from 1 mole of gold telluride to get the moles of gold alone. Then we would use the moles of gold to convert to grams. Give setting up the conversion a try, and then I'll show you the work for how I set it up. This is the first multi-step conversion we've done. Remember, let the units be your guide. We start with grams of gold telluride, so to cancel out grams, we'll put the molar mass of 452.17 grams per mole on the bottom with 1 mole of gold telluride on the top. Then we'll multiply by a conversion factor of going between moles with 1 mole of gold telluride on the bottom and 1 mole of gold on the top. Then to get to grams, we'll put 1 mole of gold on the bottom, multiply by the molar mass of gold with 196.967 grams per mole on the top, and we end up getting 217 grams of gold this way. So from 500 grams of gold telluride, we get 217 grams of gold. Not bad. So just under half of calaverite comes from gold, where just over half of it comes from tellurium. But our mole map doesn't stop there. It turns out that mole maps can be really useful for working with different chemical components and chemical reactions.